In this module, we will be seeing one of the first, so to say, applications of derivatives and the calculus we have been doing so far. This concerns figuring out when does a given function take a minimum or a maximum value or what is called an inflection point. What do we mean by this? Let's say we have a given function f of x is equal to x squared minus 1 whole squared. I invite you to go and make a table of values of different values of x and different values of y and plot it. If you do that, you will see that it looks something like as follows. This is our f of x, this is our x, and it will look like this curve that I'm going to draw over here. It will have something like this, then something over here, and something over here. So this will happen at x is equal to minus 1, this will happen at 1, and this will happen at 0. Over here, its value is 0. So you can see if you put value is 1. If you put x is equal to 0, for example, it does have the right value of 1. If you put x is equal to minus 1, it does have a value of 0. If you put x is equal to 1, it has a value of 0 again. So there are a few characteristic features of this function. This function, which just looks like some algebra I have written, is actually very common in physical chemistry. This could be what is called a double well potential, where an electron is in well 1 or an electron is in well 2 and it's jumping from well A to well B. These double well potentials are very common, and you can make it more and more complicated. It shows up in many different complicated forms. So the interesting things about this function is that you have a maximum or a maxima over here. It's a local maxima, right? It's a peak right over here. Why is it local? Because clearly this value on the left is more than what you have at this local maxima. Similarly, you can see that it has a minima here and here. These two are, however, global minima, right? Because there is nowhere else that this function takes a value smaller than these. So the question we ask us today is, how do we figure out for a given function where are the local maxima, minima, and a third thing which is called an inflection point. And the inflection point, we saw it previously. This one does not have an inflection point, but f of x is equal to x cubed, which we plotted in one of the first modules, does have an inflection point, and this is what I mean by an inflection point. It went like this, and it went like this. So if you see over here, it's a very peculiar point because it's not a local maxima, it's not a local minima, but if you were to plot the slope of the derivative of this function, it would have looked like this. What's the derivative of this function? We know that now we don't have to do any guesswork because we have mastered derivatives. F prime of x is equal to 2x squared, right? So the derivative of this is, actually I made a mistake. F prime of x is equal to 3x squared. Sorry about that. So if we plot this, it's going to look something like this. F prime of x, and if you plot f double prime of x, that's going to be 6x, and f double prime of x is going to look like f double prime of x is equal to 6x, so that's going to be just, it will pass through the origin, and that's our f double prime of x. So this point is called an inflection point. This is a point where the slope becomes 0, and we will define inflection point more carefully. So the general question is, how do we find local minima, or sorry, maxima? It doesn't have to be local or global. A given minima, a given maxima, or a given inflection point. How do we find these? How to find these without plotting the whole function. How do we do that? Is there a way to do this? And together, these three type of points, minima, maxima, and inflection point, are called extrema points. Together, they are called points of extrema. So now we are going to look at a very systematic way of figuring out, first of all, how do we know that an extremum point exists? And if it does, how do we find it? So in order to see if an extremum point exists or not, there is a very neat theorem in calculus, which is called the extreme value theorem. The extreme value theorem, which I'm going to state here without proof, although the proof is not very complicated, says the follows. It says that if a real valued function, so if we are in 1D, we are thinking about function from domain of real numbers to range of real numbers, is continuous. And by continuous, what do we mean? The left-hand limit and the right-hand limit exist and are equal to each other at all points on the closed interval. And the closed interval here is important. This means a less than equal to x less than equal to b. This is denoted as square brackets a comma b. So just an aside here, this is an example of a closed interval. Oftentimes you will see an open interval, which is denoted as round bracket a comma b. And what this means is a less than x less than b. So now, no time better than now to show you what these are, because they will show up sooner or later. So here, for this theorem, we are, however, talking about closed interval. So what it says is that if a real valued function is continuous on the closed interval a less than equal to x less than equal to b, then we must have a maximum and minimum for this function on this interval at least once. Then there must exist points C and D in this interval a comma b, and again the closed property is important here, such that f of c is more than equal to f of x for all x in the closed interval a comma b, and f of d is less than equal to f of x in the same interval. So this is exactly what we mean by, so C here is a maximum. It's bigger than every point in that interval, while D is a minimum. It's smaller than every point in that interval. So you can see how this looks like. If you have some domain A and B, and all this is saying is that if you have a function that starts here and it takes some value over here, this value could be higher than the left one, it could be smaller than the right one, doesn't matter. If it's continuous on this domain, it must have a maximum or a minimum. So you can see here for this toy function that I drew, the maximum is the black arrow, while the minimum is the blue arrow. You could imagine some other function which goes something like this. Again, you have a maximum, and actually that's not the maximum. In this case, the maximum is right where you started, right? This one is the maximum, and the minimum is right where you ended. This is the minimum. So this is a quick way to check whether we should even be proceeding with the tests that I'm going to describe next. If you have a function and you have been given a domain, and if you see that it is continuous all through the domain, then it's worthwhile to do what we are going to do next. So what is it that we are going to do next? The idea is that, so let's call it conditions for extrema. These are quite simple. They say that for a given f of x, any extrema will be at a point x is equal to x star, where df by dx calculated at that x is equal to x star is equal to 0. The first derivative must go to 0 for that point to be a minimum, a maximum, or an inflection point. On its own, the first derivative does not tell us which of these three it is. In order to do that, we have to look at the double derivative, the second derivative. If we look at d square f of x by dx squared at x is equal to x star, and then we find that this thing is less than 0. If it's negative, then together these two conditions. So it's crucial that you can't just look at a double derivative. Then what we have to keep in mind that this is together. Both of them have to be looked at the same time. If it's less than 0, that means we had a maximum. If it's equal to 0, we had an inflection point. And if it is more than 0, we had a minimum. So let's see how it looks in practice. Let's go to our example, simplest one. Actually, let's go to the one we plotted in the beginning of this module. F of x is equal to x squared minus 1 whole square. So we want to, it's a well-behaved polynomial, so we don't expect any problems of discontinuity. It's going to be continuous, so we can expect extrema to exist. So let's find them. In order to do that, let's calculate our f prime of x. What's that going to be? That's going to be 2 multiplied by x squared minus 1. So here we are using the chain rule. And then the derivative of x squared minus 1, that's going to be 2x. So this is 4x x squared minus 1. So solve for f prime of x is equal to 0. That will give us x is equal to 0. As you can see, if you put x is equal to 0, f prime of x becomes 0. X is equal to plus 1, then this term becomes 0. X is equal to minus 1, then this term also becomes 0. So 3 solutions make sense because it is a cubic. It has power 3, this one, right? So 3 solutions make sense for this problem. So, but we don't know yet which one of these is a minimum, which one of these is a maximum. In order to find that, so look how we are doing all this. We are not plotting the function. We are doing it in a very automatic way. We know how it looks like, but try to forget that for a moment. Let's see what we get, and then we'll go back and compare to what we have. F double prime of x is, we have to use the product rule over here because we have a product of 2 functions, right? So that will be 4x squared minus 1 plus 4x multiplied by 2x. And if this product rule seems confusing to you, then please go and check the previous module where we looked at product rule and other operations on involving derivatives. So this is 4x squared minus 4 plus 8x squared, or 12x squared minus 4. So now let's calculate our f double prime of x for this function at different values of x, when we are interested in specific values where we are going to check, right? So let's make a table for doing this. So what are the values we are interested in? We are interested in 0, plus 1, and minus 1. Let's proceed in a systematic manner. Let's look at minus 1, 0, and plus 1. We already know that f prime of x is 0 at all 3. So we know it's an extremum at any of these 3. Now let's look at f double prime of x. At x, actually factoring it out in this way doesn't really help us, but it doesn't hurt either. So at x is equal to minus 1, this will be 12 minus 4, or 8. The most important thing is that it is positive. At x is equal to plus 1, again it will be 8, so again positive. At x is equal to 0, however, it will be minus 4, so negative. So if you go and look at the conditions that we wrote, positive implies minimum, negative implies maximum, and we don't have any point where the double derivative is 0. So positive implies minimum. So it's kind of counterintuitive. You would think that positive should imply a maximum, but it's not. Positive implies minimum. So this is a minimum, this is a maximum, and this is a minimum. So we know that this function must have three extrema points at x is equal to 0. And this is something I mentioned in the graphing module, that looking at extreme values of functions are actually quite useful when you plot them. So we know that x is equal to 0, this function must have a local maximum. It's going to look something like this. At x is equal to, so this is 0, this is x, and we have x is equal to 1, and x is equal to minus 1, and here we have f of x. We know at the minus 1 point and plus 1 point, it has a local minimum. So you already see these are the extremum points. So even without calculating other values, now you can, with fair confidence, join these points and plot the function, which looks exactly the same. And sorry, it looks a bit asymmetric. I'm gonna call it fake asymmetry. That's my fault. But it's very similar to the shape that we actually drew in the beginning, if you recall this plot. So this is why these extremum values are quite useful. And in general, when we have a potential energy surface for a given molecule, we are interested what's going to be the molecules like to sit at a point where the potential energy is minimum. And that we can calculate if we know the functional form for the potential energy by going and looking at the first derivative or the second derivative. At the transition state, however, molecules tend to have an inflection point in the potential energy. And then we can go and calculate that by looking at the first derivative, setting it to 0, but the second derivative also to be 0. And then we get the saddle point. Later, when we do function of many variables, we will revisit this, and there it becomes even more beautiful because you start to look at surfaces, and there the inflection points themselves can have different characterizations. So that brings us to the end of this module. In the associated exercises, there are lots of problems that you can work with to gain confidence on this. Thank you very much.